we do this topic, part B, efficient polynomial evaluation. Yeah. B.1, evaluate the polynomial. So let us solve our first computing problem. Yeah. Problem number 1, evaluate a polynomial. First, I give you the problem. I describe what problem we need to solve. Okay. Given a polynomial, so it's a standard polynomial. Yeah. All right. Yeah. Yeah. So yeah, written in this way, standard polynomial. Yeah. Here, the polynomial degree n. The coefficients a0, a1 through an. Yeah. So we store the coefficients in an array. Then we have a variable. X is the variable. When we have the value of x, then we can find the value of this polynomial. So the goal, we need to find the value for this polynomial. Efficiently. So the most important thing, we need to evaluate efficiently. That means if you only find the correct answer, that's not enough. Because most of us can find the correct value easily. The issue is, can you do it efficiently? What do you mean efficiently? Here, very fast. Yeah. You should do it as fast as possible. Can you find a way to do it in the fastest possible way? That's the most important thing. Yeah. So let's try to solve this problem. All right. Here, I give you the reference in the textbook. Yeah. Here you can see in section 6.5. Yeah. So why I jump so late into our textbook? Yeah. The first reason, this topic, after I finish this one, I can assign you our programming project number 1. So next week, you can have our first project. So we can do it as early as possible. Okay, yeah. Second, the materials we take, although from a later section, but very easy to understand. Because we only use addition and multiplication. Basic operations. So we can understand everything. Yeah. All right. So let's do our first try. Yeah. Because everybody knows how to do addition and multiplication. Yeah. People just, follow the natural order to do addition multiplications. Then you can find the value immediately, right? Yeah. So that's our first try. Yeah. So we just use the straightforward algorithm. Straightforward. Yeah. So here you can see we do not need any technique, any special technique. Okay. Yeah. Because at this point, we do not know many techniques. What kind of techniques? We do not have that kind of background at this point. Okay, yeah. And this algorithm, without using any special technique, just do it in a straightforward way. We have a name for it. Later, we call this algorithm method with brute force method. Brute force method. So our first method here, we apply this brute force method. Yep. The simplest possible method. Everybody can apply it without any special background. Just use our simplest knowledge that everyone has. You can solve this problem. Yeah. All right. So let's do the work. First, let's work on each term for multiplications. Look at this general term. Can we use this? First, we have one coefficient number, a sub k. That's the coefficient number. Second, x to the power of k. So that one, we can call it monomial. Yeah, not polynomial, so single term. So this term, so it corresponds to a monomial. To calculate the value of this term, we only need to use multiplications, right? Yeah. So here you can see why we pick this general term. Yeah. Here I like to refer to this way to our previous example. Do you still remember the example we did last time, that chessboard question? When we count the number of squares, we consider k by k size, right? Look at, for the k by k size, how many squares do we have? We look at that. Think about similarity with that way. 9 minus k squared, that many squares. Here, we do the similar thing. You can see we pick a representative. So this term is the representative term because this general term can represent any term in the polynomial. If we figure out how to handle this general term, then we can handle all the terms. And similar to this chessboard counting question, that is a representative case, right? If we can answer the question for that general case, it covers all individual cases. Yeah, representative, this approach. Okay, one simple approach. Yeah. All right, here now I want to ask you our first question in this class. Can you tell me how many multiplications do we need to calculate this term using the straightforward method? One by one. You do multiplication one by one. How many you need? A little abstract, yeah, but you need to give me a number here. In terms of k, Close, yeah. First, the right direction. But the question is, you said k plus 1. K, is it possible k? K plus 1, very close, yeah. In order to fix that detail, here, first, here I treat you, it's a guess. Okay, here I treat that it's a guess, that number. But if your guess is correct, we need to verify it. All right, now to do the verification, here we apply our simple strategy, our first simple strategy. Oh, sorry, the simple strategy, yeah, just a minute, yeah. Simple strategy. So let me write here. Yeah. So because I didn't show you. Okay. The simple strategy. Try the simplest cases. Try a few simplest cases here. All right. When k equals 1, a1 times x, how many multiplications do you need? Simple. How many? A1 times k. How many? Yeah, do not use k this time. Yeah, because we already say a equals 1. All right, just tell me 1. All right, 1. So your k always correct. Okay, the answer is 1. All right, then k equals 2, a2 times x squared. How many? 2, right? And so on. All right, now a k times x to the kth. Can you tell me the number of multiplications based on your first 2 experiments here? K, not k plus 1. All right, so here we complete the verification. Don't worry, when you do your first guess, don't worry, it may not be correct. We only want to get as close as possible. Okay, so our guess, well, when you make a guess, nobody can guarantee your guess is 100% correct. Okay, we just want our guess as close as possible. But after that, we need to do the verification. We need to do some simple experiments like we're doing here. So you, after your experiments, then you come back, look at your guess, and fix it. If there is some error, then you fix it. So the answer is k multiplications. All right, that's the first step of question.
So are we not counting A0 when we do our multiplications? Wouldn't that make like k with 1? Wouldn't that be 2? Like,
yeah. All right, good question. Yeah, A0, the first term, A0, we do not need to do multiplication, right? Although A0 times 1, here, officially, A0 times x to the 0th power, right? Officially, x to the 0, that's 1. So A0, but we do not need to do it, right? If we can save one multiplication, we want to save, we like to save, right? So we count the zero number of multiplications. Number of multiplications, 0. Okay? Yeah, 0 corresponds to the subscript 0, same number. Another question? Yeah. Yeah, right. X squared, right? Okay. Right. Yeah, 2. Yeah. So right here, 2 multiplications.
X squared is right as multiple of
X squared in right. Yeah. X squared, 1 multiplication, but you need to multiply the coefficient. Another one, number 2. Yeah. All right. Yeah. So we finish our first step. Okay. Yeah. Second. Yeah. All right. Yeah. The question, is your algorithm efficient? Yeah, here. Yeah. we find the right answer, or so not right, yeah, so let's say in this way, we find a way to give us the correct answer. Yeah, find the correct value of each term. Yeah. All right. The question is that the fastest possible way? Because our goal, we want to find the fastest possible solution for this problem. The way we're doing here may not be the fastest. Can you think about that? Is there another possible way we can do a little faster? Can you imagine that? So here we have a chance to think about that question. Can we do a little better than what we are doing here? All right, yeah, yeah, all right. So here, that question is a relatively big question. So we do not need to give the answer at this point, but I raised that question first. Later at some time, I need to answer that question. Here, I just raise it. Okay, all right. So then another question we also want to ask here, yeah. Find the performance measure. When you say fast, slow, actually you need a performance measure, right? You need to define some specific measure to measure performance. How fast, how slow? You need some measure. The question is, what is a good measure? What is a fair measure? Okay, or another way, what is a stable measure? Stable measure. Yeah. So we need to get a stable measure. Stable. Okay. What do you mean stable measure? Here you can imagine the first straightforward measure is the response time, right? When you write a program, here, let's write a program to evaluate the polynomial. Yeah. So then we need to run it. When we run this program in our computer, we can look at the response time. That's our first performance measure. First performance measure. But that measure here we treat it's not stable. It's not stable. Why I say not stable? Because it relies on hardware, computers. Because when you run your program on different computers, the response time could be different. Think about that. On supercomputers, on some very old computer, the response time could be different. So we treat that measure is not stable. Here we want to find a stable one. No matter you run on a supercomputer or ordinary, old computer, you get a same measure number, same performance measure number. No difference. That kind of stable measure, we need that. Yeah, think about that. Yeah. Our requirement. Yeah. Okay, all right. Another question, are we satisfied with this solution? At this point, that's the only solution we have, right? Because we do not know the second solution. If we have no second choice, that's the only one we can take. right? Yeah. So to answer this question, first, we need to find the second solution first. Then we can say if we are satisfied with our first solution or not. Okay, yeah. So some of question we need to delay, but we raise those questions first. Yeah. We need to spend some time to get good answers for these questions. Yeah. All right. All right. Yeah. So still long way to go. We need to do a lot of analysis before we can answer these questions. Okay. All right. All right. Next, now let's do analysis. Yeah. Do we really need an algorithm here? Yeah, because if we just do that brute force method, we may not really need some special algorithm. Yeah. If you feel the current one, the brute force one, is good enough, why you need another advanced special algorithm? Yeah. But for us, here we are learning this algorithm class. So we should have our thinking in this way. After we solve a computing problem, we always need to ask us this question: can we improve it? Can we make it faster? Well, so that's the first question we should ask after we solve one particular problem. Yeah. Here, we need to try it. We need to try to improve it. Yeah, all right. Here, before we can improve it, here, the first thing, we need to know, we need to find some specific performance number to describe the efficiency of this algorithm. Then we can talk about improving or not, right? If you do not have any specific description on this current algorithm, how do you talk about improvement or not, right? So we should get our performance measure number first. Then we can look at if we can improve it. So our performance measure question comes out. How do we measure our performance? Yeah. All right, so here we know we only do additions and multiplications, these two operations. And we want to use a better measure than that response time. It's unstable. So we want to have a stable measure. That stable measure does not rely on different hardware, or other factors. Yeah. Programmers' experience, that's also another factor. Think about, even when you implement the same algorithm for an experienced programmer and for a beginner programmer, they may implement in different ways. And the performance could be different, right? Yeah, so that's another factor, making the response time unstable. Here, we want our measure does not rely on those factors. Yeah, okay. Now, here, there is one way we can get this stable measure. How about counting number of operations? counting number of operations, number of additions, number of multiplication. It does not rely on hardware, right? Yeah. You run on any machine, you need to do the same number of operations, right? Yeah. Also, for programmers with different background, you also need to do the same number of operations, right? Yeah. So here we take this approach, this objective approach. Yeah. All right. Yeah. So we feel it's better than execution time. Yeah. So we already discussed if the execution time not stable. Yeah. All right. Yeah. So here, the next question, how to measure efficiency? Yeah. So this time we feel the improvement is use the number of operations. All right, yeah. Use the number of operations. But the question, we have two types of operations, addition and multiplication. Which one we should use here? Okay, yeah. Because we know inside a computer, the time used for an addition and for multiplication different. So when you want to use number of operations, which one you should use? Another question. Okay, or both. Can we find a way to use both? But if we use number of operations, both operations, is it a fair way? Addition, we have that one addition, number one. Multiplication, we have number of operation one. Can you do 1 + 1, 2 operations? That's not good, right? One addition plus one multiplication, you cannot say 2 operations. If you say 2 operations, because these 2 operations will be different from 2 multiplications, right? 2 multiplications, you get a 2, but 1 addition plus 1 multiplication, you have 2, but these 2 numbers should be different. How do you establish some fair ground to do comparison? We want to do fair comparison. Okay, yeah. So that question we need to answer. Yeah. In our next slide, we will answer that question. Okay, all right. Yeah. So here, using number additions, multiplications, but then we need to do something special in order to consider both operations together. Yeah. All right. Yeah. Okay. We need some special assumptions. We do some assumptions so that under these assumptions, then we can integrate additions, multiplications in a fair way. That's our goal. Yeah. So what kind of assumption? Yeah. I make here. Yeah. Let's assume each addition takes 1 unit of time. Time unit. Certain amount of time. Yeah. Yeah. Just 1 unit. Okay. Yeah. Yeah. Then each multiplication takes 10 units of time. 10 times. Yeah. So here, this number, although I choose 10 here for convenience, yeah, but But actually, in the real world situation, when we look at computer CPU, close to 10-to-1 ratio, okay? Not exactly 10-to-1, but very close to 10-to-1. The CPU time needed for one multiplication approximately equal to CPU time needed for one addition. Think about that. That difference, pretty big, right? 10-to-1 ratio, pretty big. Yeah. So that's what happened in CPU. Okay, yeah, 10-to-1 ratio. So we add this reasonable assumption. Close to the real world, but not necessarily exactly the same. But it's good for our discussion here. All right. So with this simple assumption now, we can integrate additions, multiplications. We can measure them in number of time units. How about that? Number of time units. Okay, yeah. So now we get a stable measure, yeah. And it's a fair measure, right? Also fair measure. Okay, yeah. All right. Now our goal becomes find the number of time units for our first method. Okay, all right. Yeah. Here, although I say time unit here, yeah, but you may wonder how large is that time unit, right? Yeah, here I can give you the idea. Unit here, certain number of nanoseconds. Nanoseconds. Do you have idea how large is a nanosecond? Nanosecond. Okay, yeah. So we start from 1 second, then 1,000th of 1 second, millisecond, right? 1,000. Another 1,000th microsecond, right? Microsecond. 1 millionth, that's 1 millionth of 1 second, microsecond. Then another 1,000th, 1 billionth of a second, nanosecond. 1 billionth of a second. Yeah. Here representing in this power of 10, 10 to the negative 9th power. That's the nanosecond. Yeah. One addition takes certain number. Yeah. 2 or 3. Yeah. 2 something, around 2. Around 2. 2 something nanoseconds, approximately. That's how fast in a modern CPU. Okay, yeah. But here we do not need to get to that details. We just count the number of units. All right. Let's do analysis. All right. Here we have this reasonable assumptions. Yeah. So we feel comfortable because we have a stable measure. We have a convenient stable measure. So now we can calculate the number of time units. Yeah. All right. All right. Yeah. And this small, simple assumptions, it would not change our question significantly, right? Yeah. Still, we solve the same problem. We didn't change the problem. Same problem. Yeah. All right. Yeah. But in our discussion, it's much easier, right? When we do discussion, now we can, do the calculation in a more convenient way. Yeah. All right. All right. Yeah. So that's our first round discussion. Yeah. Okay. Then the second round. Yeah. So at this point, so basically I give you the background of this question. Yeah. So what are those possible questions we need to think of? Yeah. So here you have an idea. We haven't answered those questions, yeah, but that's our first round. Now let's move to the second.